Did we finish this one or not? I think we were working on it, right? Did I finish last time, or did I stop in the middle? Oh, we didn't do it? Okay, okay, okay. Okay, so we have R134A refrigerant at 600 kilopascal and 150 degrees Celsius is in a spring-loaded piston cylinder device. So we have spring-loaded piston cylinder device, and there's R134A. Initially, T1 pressure is 600 kilopascal. Temperature T1 is 150 degrees Celsius. And the volume at the initial state is 0.3. So V1 is 0.3 cubic meters. And we have a cooling process. So heat is removed. Because of this cooling process, the temperature drops to minus 32 degrees Celsius. T2 is minus 32 degrees Celsius. V2 is 0.1 cubic meters. We want to determine the heat transfer and the energy transfer by work. Okay, so if we write the energy balance equation, Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work, WB. So in this equation, we have heat transfer from the system to the outside. So we have Q out. If you have Q out, there is no Q in because heat transfers from a higher temperature to a lower temperature. There is no heat transfer from a lower temperature to a higher temperature, according to the second law of thermodynamics. And there is no information about energy transfer by work other than this moving boundary work. So we just need to determine Q out and WB. So these are what we want to determine in this problem, okay? So Q out is what we need to determine. So we need to find mass, U2, U1, and WB. So let's find the mass first. If you look at the initial state, we have pressure and temperature and volume. If you know pressure, and this pressure is an intensive property, temperature is an intensive property. However, this volume is an extensive property. The difference is these are independent of mass, and this one is dependent of mass. So if you know pressure and temperature, you can determine another intensive property, which is specific volume. So if you determine specific volume, V1, you can compare this specific volume and this actual volume to determine the mass of the system, okay? So let's analyze this initial state first. So we have a pressure and temperature. Then the first thing we need to do is we need to determine the phase change process at the initial state. So since we know pressure and temperature, and we have this pressure diagram, so why don't we make T V diagram at 600 kilopascal. TV diagram looks like this. To complete this TV diagram, we need to know T set, saturation temperature at 600 kilopascal, and VF, the specific volume of saturated liquid and the specific volume of saturated vapor, which is Vg. On this TB diagram, we have number 1, compressed liquid, number 2, saturated liquid, number 3, saturated mixture, number 4, saturated vapor, number 5, superheat vapor. Then let's find T-sat Vf Vg. The pressure is 600 kilopascal, and when it is 600 kilopascal, saturation temperature is at 600 kilopascal, the saturation temperature is 21.58. I'm going to write here 21.58 degrees Celsius. That's the saturation temperature. And the temperature of this system at the initial state is 150 degrees Celsius. So let's find this temperature on this TB diagram. This vertical axis is the temperature, and 150 degrees Celsius is up here, greater than T-sat. So the only possible phase change process is number 5, superheat vapor. So this is 150, and we have superheat vapor at the initial state. Once you know this is a superheat vapor, you can find the specific volume from superheat vapor table, which is right here. Table A12, superheat vapor table for R134A. And we have 600 kilopascal, and we have 150 degrees Celsius. So if you want to determine specific volume, this is what we need, 0.0555. So lowercase v1, the specific volume at the initial state is 0.0555. What is the unit? Cubic meters per kilogram. Cubic meters per kilogram. Then this V1 is mass times specific volume. And we know specific volume is this one. And we can determine the mass of the system. From here, the mass of the system is 5.4. Okay. What about U1? Since we know we have to use this property table for the initial state, we can find U1, and U1 at 150 degrees Celsius, 0.6 megapascal is this one, 359. So this is U1. U1 is 359.21 kilojoule per kilogram, directly from table A12. So now we have the mass of the system and U1. Then the next one is going to be U2. So how can we determine U2? Then you can check the properties that we know at the final state. We have temperature and volume. However, this volume is not going to be used because this is the actual volume. We need specific volume to evaluate the final state. So how can we do that? We know the mass of the system. So the specific volume, V2, can be determined by the actual volume, V2, divided by mass. So the V2 is going to be 0.1, and the mass is 5.4. So we can determine the specific volume at the initial, at the final state. That is 0.0185 cubic meters per kilogram. Once you know the temperature and the specific volume at the final state, now we can evaluate its phase change process. How can we do that? We need to make another property diagram. PV or TV. In this case, we only know the temperature. We do not know the pressure of the system, so we can only make PV diagram at this temperature. So when temperature is minus 32 degrees Celsius, we can make PV diagram. This one looks like this. You may ask, why can't we use this property diagram at the final state? The phase change process changes between the initial and the final state. So you cannot reuse this property diagram because this property diagram is only valid at the initial state. There is another property diagram we have to use for the final state. Then, to complete this PV diagram, we need to know P set, VF, and VG. Where can we find P set, VF, VG? From this temperature. That means we need to go to the temperature table. Table A10, properties of saturated R134A temperature table. And what is the temperature? Minus 32. So here is minus 32. And we need to know P set, VF, VG. P set, VF, VG. So these are the numbers that we are looking for. So let me write these three. On this PV diagram, P set is 77.04 kilopascal. VF is 0.7172 times 10 to minus 3. Remember that these values are after multiplying by 1000. So the actual value of this specific volume should be this one divided by 1000. And VG is 0.2451 cubic meters per kilogram. And on this PV diagram, there's a compressed liquid, number 1, saturated liquid, number 2, saturated mixture, number 3, number 4, and number 5. So I guess we are ready to determine the phase change process. We used minus 32 to complete this PV diagram. And now let's use the other property that we know, which is specific volume. The specific volume is the horizontal axis. So let's find 0.0185 on this axis. VF is 0.7 times 10 to minus 3. This number is too low. VG is 0.24. That is greater than this number. So the specific volume of our system should be between VF and VG. So what is the phase change process? Number 3, saturated mixture. Once you know it is saturated mixture, when you have saturated mixture, there's one more property that you need to evaluate, which is quality X, the ratio between liquid and vapor in the mixture. So how can you determine this quality X? You can use linear interpolation. Since we know specific volume, so let's use V. So V is VF plus quality X times VG minus Vf. And we have Vf here, Vg here. This specific volume at the final state is this number, 0.0185. So we have everything but the quality X. So you can determine the quality X. If you do, the quality X is 0.073. Then once you determine the quality X, now we can evaluate any other properties of this saturated mixture. And what we need to know specific internal energy, U2. So if you want to determine U2, then you can use the same equation in terms of U. So U is UF plus quality X times UG minus UF. And quality X is given. We just need to find UF and UG from the same property table, table A10. Now this time we need to know UF and UG. So these are the numbers that we are looking for at this temperature. So 9.47, 209.01. So what is U? We can determine that, right? So U is 23.99 kilojoule per kilogram. So this number goes here, 23.99 kilojoule per kilogram. So we got mass, we got this mass and U2 and U1. So if we determine this WB, then we can determine the heat transfer. So let's find WB. There are 5 phase change processes. The first one is constant volume process. Number 2 is constant pressure process. Number 3 is constant temperature process. Number 4 is polytropic process. However, this process is none of them. So we can use the graph method. So the last way to determine the moving boundary work WB can be used, we can use PV diagram. So that means that we need to know the initial pressure, initial volume, and the final pressure and the final volume. So what is the initial pressure? 600. So up here, 600. What about the final volume? 0.3. So here, 0.3 cubic meters. So the initial state is right here, number 1. What about the final state? We know volume 0.1. What about pressure? At the final state, we have saturated mixture. Then the pressure of saturated mixture is going to be the saturation pressure. So the value is 77.04. Down here, 77.04 kilopascal. So here is the final state, number 2. I think we discussed, when we have a spring-loaded piston cylinder device, the relation between number 1 and number 2 on this PV diagram is a straight line. Let me just show you one last time. So when we have spring-loaded piston cylinder device, if we analyze all the forces acting on this piston, we can first consider spring force this way and the atmospheric pressure PATM and the pressure by our system, so the unknown pressure P, and the weight of the piston W. So if we say upward is positive, assuming that downward is the direction of gravity, the sum of forces should be 0. Then we can consider the spring force downward, so that's a negative direction. So minus spring force. Then how can we determine spring force? Spring constant K times displacement X. So minus Kx, and the weight of the piston minus W, and the atmospheric pressure. But this is pressure, not force. So if you want to determine force from this pressure, force is pressure times the cross-sectional area. The cross-sectional area, this area. So then minus PATM times area. Now we have a pressure by our system plus pressure of our system times area. If you rewrite this equation in terms of this pressure, P is PATM plus K, the spring constant, divided by area times X plus W, the weight of the piston, divided by area. So that's how we can determine the pressure of our system. And if you look at here, this atmospheric pressure is constant. Spring constant is constant. Area is constant. Weight is constant. Area is constant. So the pressure of our system is going to be simply some constant times this displacement X plus another constant. So this is a first order. So if we find the relation between number 1 and number 2 in terms of pressure, it should be a straight line. Then if you know it is a straight line, we can determine the area under this process. And how can we do that? This one is 600. This one is 77.4. This is 0.2. So the area, oh, this one looks ugly. So the area can be determined by 77.04 plus 600 divided by 2 times 0.3 minus 0.1. So that's how you determine the area. If you do, the area is going to be 67.704 kilojoule. Then the area is the moving boundary work. So this WB is 67.704. So this number goes up here, 67.704 kilojoule. So we have everything in this energy balance equation except the heat transfer. So we can determine the heat transfer, right? However, there is one mistake that I made in terms of this moving boundary work WB. What is it? When you determine this moving boundary work, especially from this PV diagram, when you calculate this area is going to be always a positive number. Then you need to determine the sign of this moving boundary work. If it is an expansion process, this moving boundary work is positive. If it is a compression process, this moving boundary work WB is a negative value. So if you look at here, initially it was 0.3 cubic meters, and finally it is only 0.1 cubic meters. So it is a compression process. Therefore, you need to add negative sign here, minus 67.704 kilojoule. And then if you to solve this energy balance equation, you can determine this Q out. And if you do, this Q out is 1,879.7 kilojoule. So this is the heat transfer. This is the energy transfer by work, which is the moving boundary work. Okay, that's how you solve this problem. Any question? If I give you this problem in your second exam, can you solve it? So this could be the hardest problem. So if you can solve this one without any difficulty, I think you're good to go in terms of chapter 3. Okay. Like the final boss when you play a video game. So this problem is the final boss in chapter 3. So the way you prepare for the second exam is pretty simple. We already solved many problems in this chapter, and you have a homework assignment. So keep solving those problems until that you are completely, comfortable solving those problems. Then I don't think there is any problem in the second exam, because as you experience from my first exam, you can see the problems in my exams are pretty similar to the problems that we did in the classroom or in the homework assignment. Okay. Any question? No? Yes. Homework 3? Not yet, because we haven't finished chapter 3 yet. So once we finish chapter 3, the homework for that chapter is going to be a week after we finish that chapter. So if we finish chapter 3, that's my original plan, then we have a homework due next Tuesday. If we cannot finish this, but if we finish this chapter 3 this Thursday, then the homework for chapter 3 is going to be due by Thursday next week. Oh, that's wrong, because Even though we finished chapter 3 today, there's no due on Tuesday next week because we have a break coming. Full break. Isn't it nice? No? I won't be here. I will go somewhere. I'm planning to go to, the Chicago. Sometimes, yeah, I like Chicago. So whenever I have time, that I go there. Maybe, the once a month or so. Yeah, it's a lot. Yeah. Oh, it's only 4 hours. Only 4 hours. I like driving. So when you get bored, then, to make, your driving, the fun, you can, to buy a new car. Then it's going to be fun, right? I was kidding. I like Chicago because they have many, many interesting museums, Science Museum, Field Museum, Adler Museum, and Shedd Aquarium, etc., etc. If you have a membership in any of the museum in Michigan, you can get the admissions there for free. You know that? Yeah. You didn't know that? There's something called ASTC, American Science and Technology Passport Program or something. So if you have a membership in a museum that is a part of this program, then you can get free admission to any other, the museums in the same, the membership, but it should be 90 miles away from your home museum. So if you buy a, the membership, let's say, the Midland, the museum or Lansing Museum or Grand Rapids, you can get all museums, not more, most of them in Chicago area or, the other, the states for free. You didn't know that? Good to know, right? So there's a membership program in museum. There's a membership program in zoo and aquarium. So there's a membership program in children's museum. So or science center. So there are many, the opportunities available at discounted prices or free. So this is the next problem. We have a 2 kilograms of saturated liquid R134A with an initial temperature of -4 degrees Celsius. It's contained in a well-insulated weighted piston cylinder device. This device contains an electrical resistor. Okay, so we have energy transfer by work. That's electric work. We know how to determine this electric work. The voltage times current times time is going to be electric work. If you want to determine electric power, it's going to be voltage times current. We studied that in chapter 2. We want to determine the time required for the refrigerant to be converted to a saturated vapor and the final temperature. Okay, we can do that. No problem. Only one table. Looks like, the much simpler than the previous problem. So we have weighted piston cylinder device. There's one thing that we need to know, if we have a weighted piston cylinder device, if we make one assumption between piston and cylinder, if we assume that this one is frictionless, then what kind of forces acting on this piston? We can think about the atmospheric pressure, PATM, P atm, and the pressure by our system acting on the bottom surface of this piston that is unknown P. And what else? We know we have the weight of the piston. This way, W, weight of the piston. Then let's do a force analysis. The sum of forces should be what? 1, 2, 3, -1, -2, -3. Let's say if it is a positive value, then what's going to happen? We don't know unless we determine the direction of this force analysis. So let's assume that the upward direction is positive. Then, if this sum of forces is a positive value, that means the net force is upward. So this piston is going to move upward continuously. If the sum of forces is less than 0, that means that the net force is a negative value, so it moves downward continuously. Either way, they don't make sense, right? So the sum of forces should be 0 to maintain the position of this piston. So the sum of forces should be 0. Then let's consider, all the forces acting on these pistons. First, we have a weight, and that's a negative direction. We assume that upward is positive. A weight is working on downward, so it's a negative W. What about this pressure by our, the system? P, but P is not force, so we need to multiply by area. Pressure times area is force. And we have atmospheric pressure, the acting on the top surface. So the direction is downward, so it's a negative. Pressure times, atmospheric pressure times area. So that is the force analysis. So let's rewrite this equation in terms of the pressure of our system. So this P, so P is W divided by area plus atmospheric pressure. So let's check which one is a variable, which one is a constant. This P of this R134A, we have no idea. What about this W? We know, we do not know what is the weight of the piston, but we know this weight should be constant. Area should be constant. Atmospheric pressure should be constant. So what does it mean? The pressure of our system should be constant. So whenever you have a weighted piston-centered device, if you assume that there is no friction between the piston and the cylinder, then you can say it's a constant pressure process. If you know it is a constant pressure process, what is the moving boundary work? Oh, not the moving boundary work. If you know it is a constant pressure process, how do you write the energy balance equation? The energy balance equation, the general form, just for your information, the energy balance equation for a closed system, Q in plus W in minus Q out minus W out. By the way, these can be rewritten as Q minus W if you only consider net heat transfer and net energy transfer by work. So this one is Q net, W net. Anyway, the right-hand side should be mass times U2 minus U1 plus moving boundary work. And if you have a constant volume process, constant volume, the right-hand side is mass times U2 minus U1. If you have a constant pressure process, this is the constant pressure process, then the right-hand side of this equation is mass times H2 minus H1. H is enthalpy. So this is the general energy balance equation for a closed system, and we know the pressure is constant because we have a weighted piston cylinder device without any friction between the piston and the cylinder. So the energy balance equation we are going to use is this one. Then let me write this energy balance equation here. Q in plus W in minus Q out minus W out is mass times H2 minus H1. Okay? Then we are ready to solve this problem. We have the governing equation, and we just need to evaluate each term one by one. Okay? First, it says that this piston cylinder device is well insulated. What does it mean? If it is well insulated, the name of the system is adiabatic system. We studied it in chapter 2. Adiabatic system means there is no heat transfer. So this is an adiabatic system. There is no heat transfer. And we have an electrical resistor is providing work into the system to determine whether it is an incoming energy transfer or outgoing energy transfer. Just think, whether this, the electrical resistor heat the system or cool the system. When electric resistor works, it's going to generate heat that is going to increase the temperature of this refrigerant. So it's a incoming energy transfer. So W in, not W out. Then how do you determine this electrical work? Electrical work. We can use voltage times current times the time is the electrical work is mass times H2 minus H1. So what is the voltage? 10 volts, 10 volts. And what is the current? 2 amperes. 2 amperes times T is the unknown. What about the mass? 2 kilograms. H2 minus H1. Initially, it is saturated liquid at minus 4 degrees Celsius. How do you determine H when you have a phase change process number 2? HF at the given condition. What condition? Minus 4 degrees Celsius. Now, the refrigerant is going to be converted to a saturated vapor, saturation phase change process number 4. So how do you determine this H value? This is going to be Hg this time because it's a saturated vapor. And what condition? This minus 4 degrees Celsius is the saturation temperature, right? So do you think the saturation temperature changes between the saturated liquid and saturated vapor? No, they don't. Between saturated liquid to saturated vapor, they are both T set. So temperatures do not change. So this Hg should be at minus 4 degrees Celsius. So can we determine Hf and Hg at minus 4 degrees Celsius? Yes, we can. From where? From this table A10. Where is the Hf? Where is the Hg? Minus 4 degrees Celsius is here. So what is the number we are looking for? This one for Hf, this one for Hg. So Hf is 44.75. Hg is 244.9 kilojoule per kilogram. Kilojoule per kilogram. Okay? So if you solve this equation, you get how much time is required. Then let's see, 10 2. So it's 20 times temperature time t is going to be 2 times 244.9 minus 44.75 multiplied by 2. So we get 400.3. 400.3. So this time t should be 20 seconds. Is this right or there's a mistake? We all know there is a mistake, right? You just need to find it. Where is it? Extra credit? 0.1. That's cool. That's more. Better than nothing, right? That's correct. So this one is kilojoule per kilogram. When you multiply voltage times current, just joule, not kilojoule. So this one should be either multiplied by 1000 on the right hand side or divided by 1000 on the left hand side. So how much time is required? The long time times 1000. That much time is required. Okay. Any question about this problem? So whenever you do a calculation, especially when you have a kinetic energy, potential energy, electrical work, so anything other than heat, the unit is usually joule rather than kilojoule. So be careful when you calculate electric work or kinetic energy or potential energy. The rest of the heat transfer, they are kilojoule, but the other energies are usually in joule. So you need to make sure that you use the right unit. Point 1 point. Okay, so previously we solved the two problems using phase change material, and you may remember, that we studied two different systems. One is phase change material, and the other one is just pure system, like the pure gas, pure solid, or pure liquid. And we learned the one equation to study this pure system, that is the ideal gas equation. But the ideal gas equation can only help you to determine the relation between pressure, volume, and temperature. What about if you want to determine specific internal energy U, specific enthalpy H? Then how can you do that? We can use specific heat. Then what is the specific heat? There are two specific heats. The first one is specific heat at constant volume, CV. The other one is specific heat at constant pressure, CP. So the energy required to raise the temperature of the unit mass of a substance by 1 degree when volume is constant, that's a CV. When pressure is constant, that's a CP. So how much energy is required to raise the temperature of this system by 1 degree when the system is just 1 kilogram? That is specific heat at constant volume process and constant pressure process. Then why do we have CV and CP rather than just one specific heat? If you remember the energy balance equation for a closed system, then we have these two. Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. This is the general energy balance equation for closed system. But if you have a constant pressure, constant volume, we have mass times just U2 minus U1. Or if you have a constant pressure, then it's going to be just mass times H2 minus H1. Then we can use the CV at constant volume. We can use CP at constant pressure. So we can use CV for constant volume. We can use the CP at constant pressure. So to determine U, to determine U2 minus U1, we use the CV. To determine H, H2 minus H1, we use the CP. So this is how we use these specific heats. U2 minus U1 is CV T2 minus T1. This is one equation. The other one, H2 minus H1, is CP T2 minus T1. So that's how we use specific heat to determine the change in specific internal energy, the change in specific enthalpy. That's it. That's everything you need to know in terms of specific heats in this chapter. Okay, these two. You can write them down on your formula sheet. That's all. If you go to the next slide, the slide, you can see there are, the specific heat relations, such as, the specific heat relations of ideal gases. These are important, but not in this chapter. So we are going to study them later when we go to chapter 6, because we want, use these relations until chapter 6. So it will be much more convenient if we study them, at the beginning in chapter 6. Okay. So that's everything in terms of theory in chapter 3. So we studied how to evaluate a property of phase change material using the table. Let me give you a summary. So in chapter 3, we studied there are two different materials, phase change materials and pure system, like a pure gas, pure solid, pure liquid. So the first part we did is how to evaluate their properties. So when we have a phase change material, we use the table. You remember the table problem in exam 1. So that's how you evaluate a property of phase change material. Then what kind of phase change materials that we are going to study? And we have studied before. Water, H2O, and refrigerant, R134A. So these are the most common, one of the most common working fluids in engineering systems. Water and R134A. So to evaluate, let's say, specific volume, specific internal energy, specific enthalpy, we use this table. For this pure gas, pure solid, pure liquid, we used PV is RT, or PV is MRT, that's for gas, and we use the specific heat. U2 minus U1 is CVT2 minus T1. H2 minus H1 is CPT2 minus T1. So that's how we evaluate their properties. Once you evaluate their properties, then you can use energy balance equation. Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. If you have a special process such as constant volume process, this is going to be mass times U2 minus U1. If it is constant pressure process, it is mass times H2 minus H1. So these are a summary of what we studied in chapter 3. Of course, there were the 5 different ways to evaluate this WB. So the first one is when WB is so to evaluate WB, when we have a constant volume process, WB is 0. When we have constant pressure process, WB is PV2 minus V1. When we have constant temperature process, WB is PV natural log V2 over V1. When we have a polytropic process, WB is P2 V2 minus P1 V1 over 1 minus n. And finally, none of them works. Then we can use a graph, PV diagram, and calculate the area. So this is a summary of what we studied in chapter 3. The first exam covered this much. So the second exam is going to cover the other half. How to use this energy balance equation using this moving boundary work for a closed system. Could be one question in your second exam, right? So that's a summary. That's not the end of the chapter 3. We still have many problems to solve together to use this energy balance equation, especially when we have a pure system. But it's good to know to see the overview of this chapter so you get the whole picture. We have 10 minutes, so let's solve a few problems. using pure system and using this energy balance equation. So here is another spring-loaded piston cylinder device. I wish that we have a bigger screen than this one. My dream classroom has, the screen. Every wall is my screen, like an IMAX classroom. Spring-loaded piston cylinder device contains 1 kilogram of carbon dioxide. So we have, I have these tables. So the number one, spring-loaded piston cylinder device contains 1 kilogram of carbon dioxide. This system is under a heating process from 25 degrees Celsius to 300 degrees Celsius. We want to determine the total heat transfer to and work produced by the system. Okay, we can do that. First of all, when you see this spring-loaded piston cylinder device, what does it mean? It means please use PV diagram to determine its moving boundary work. So to determine moving boundary work WB, we have to use this PV diagram. I don't have to explain that, right? Because we did a spring-loaded piston cylinder device in one of the previous problems. The first problem we did today. And it's a closed system, so we can use energy balance equation. So what is the energy balance equation? Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. Is it a constant volume, constant pressure? None of them. So we have to use this general energy balance equation for a closed system. Then this is a carbon dioxide. Previously, I told you that when you have a pure system, pure gas, carbon dioxide, how do you determine U2 minus U1? We can use a specific heat, CV, T2 minus T1. Okay, sounds pretty simple. So let's do that. Instead of U2 minus U1, we can use CV, T2 minus T1. Mass times specific volume at constant, specific heat at constant volume, T2 minus T1 plus moving boundary work. And we want to determine the total heat transfer to and work produced by the system. So total heat transfer to the system, that means Q in. So there's no Q out. And there's no information about any other work than the moving boundary work. So it means that we want to determine Q in and WB. What about the mass of the system? 1 kilogram. CV, where do we get this CV? We can find this CV from a table, table A20. T2, initially 25, and finally 300. So we just need to evaluate CV and WB. So let's find CV first. CV of carbon dioxide can be found from this table, table A20. Then where is the CV? This one. So there are many numbers, over 10 different numbers. So which one are we going to use? Just randomly select one of them? Of course not, right? And what is the condition? Temperature. Oh, we have a 25. and 300. So should we find 25 and select the specific value at 25? No. 300? No. Then what is the reasonable way? The average temperature. So let's find the average temperature. Between 300 and 25, the average temperature, T average, is 162.5 degrees Celsius. So let's find this value. Oh, 162.5 is less than 250. Oh, we don't have any value here. No, that's not the case. The unit of this temperature is Kelvin. The unit of this temperature, average temperature that we calculated in degrees Celsius. So let's use Kelvin plus 273. So what do we get? 435.5 Kelvin. Then you need to evaluate CV value at this temperature. It's going to be between 0.75 and 0.79. I don't know exactly, but you can find this value between these two. Let's say approximately 0.77, but you need to determine this value by linear interpolation. Okay. And we have everything but moving boundary work. Then how do you determine moving boundary work? By the way, this one is from table A20. What about moving boundary work? Oh, we need to know the pressure and volume at the initial state and at the final state. So how can we do that? We know the pressure and temperature. So if you know pressure and temperature, you can determine the volume at each state. By how? By using PV is MRT. So we can apply this PV MRT at the initial state and again at the final state. You cannot just use only one PV MRT for both initial state and the final state. You can only apply this PV MRT at a state. So it's going to be initial state and the final state, P2V2 MRT2. Why there is no M1, M2? Because it's a closed system. M1 is the same as M2. Why there is no R1 or R2? This is carbon dioxide. There's only one carbon dioxide. Then, what is the mass? 1 kilogram. T1, 100 kilopascal. T2, 1000 kilopascal. Mass, 1 kilogram. What about the gas constant? Gas constant can be determined by universal gas constant R bar divided by molecular weight. So universal gas constant is always 8.314. What is the molecular weight? The molecular weight of carbon dioxide is 44.01. 44.01. So what is the temperature? The initial temperature is 25 and 300. So I'm going to write 25 and 300. Right? No. Kelvin, right? 25, 273. 300 plus 273. Then you can get V1, V2. If you do, V1 is 0.5629 cubic meters. V2 is 0.1082 cubic meters. Then let's find P1 is here, and this one, this is number 1, 0.1082, 0.5269. So this is 100, this is 1000. So we have number 2. We know it's a spring-loaded piston cylinder device, so it's going to be straight line, and you just need to determine the area under this line. The area is going to be 250.1 kilojoule. So this 250.1 kilojoule goes here, and we can determine Q in. Am I right? No, because it's a compression process again at -1. So this one is going to be minus 250.1 kilojoule. And if you do the calculation, Q in is minus 69.4 kilojoule. So what does it mean? Minus 69. We thought that it's a heat is added to the system, but after this calculation, we learned that it is actually removed from the system, because that's why we have a negative sign. Then why there is a temperature increase? Because of the compression process. The compression process increased the temperature, but that's too. And also there was a heat removal of minus 69.4 kilojoule. Okay, so that's how you solve this problem. Any question? No? Then we will continue, in the next problem this Thursday. Thank you. Now, if we finish chapter 3 this Thursday, then the homework 3 is going to be due by Thursday.